Okay, good morning, everyone, and welcome to this year's edition of the Dynamic Structural Econometrics Summer School. My name is Dennis Christensen. I'm one of the local organizers, as you may well know. The other organizers, local organizers, should also be somewhere here. Oreo de Paula is down there, and Lars Nesheim is somewhere in the building. Yeah. Anyway, without further ado, very welcome here to an exciting 7 days of structural econometrics. The first lecture, oh yeah, maybe I should also introduce the core teaching teams. So this is Bertel Scherning from University of Copenhagen, Fyodor Ishkikov from Australian National University, Bob Miller from Carnegie Mellon, and then, unfortunately, John Vost has gotten ill, so he had a medical emergency, so he will not be able to join us. He will not be. He was scheduled to teach tomorrow, so we're still sort of trying to figure out how to how we're going to sort of the format of his lectures will be. So more about that later. But unfortunately, John will not join us. Victor Aguirre will join us, but hasn't arrived yet. So he should be here from tomorrow. So you can get to see more of Victor from there on. Yeah, you can sort of see the schedule here with Victor and John for Tuesday. So before the first lecture, before Bob starts with the first lecture, I think Fyodor would like to say a few practical details to share with you.
Yeah, so great to see everybody here. Thanks for coming. I wanted to talk a little bit to bring everybody on the same page with the technical details. I'm sure that a lot of you had already checked the internal page. Let me just go through the website quickly. So over here, you know the password. Show of hands who knows the password there. Very good. You can bookmark the page on the other side, so you just access it later. I want to highlight this Zulip chat. If you haven't already, please go there and register. We will have hopefully an active discussion following each lecture and then conference presentation. You're very welcome to ask questions in writing in chat. Of course, this is done also for the online participants. You know, as lecturers would prefer, ask questions as we go along, but there's also this option in chat. And we will use the chat to make kind of the real-time announcements if we have to. You are also welcome to start discussions between yourselves. So everybody is able to start a new topic. I don't know if you want to make plans for the evening or something like that. You're all welcome to use this. That's the first thing I wanted to say. And the other thing I wanted to say is teaching materials. So we have both Dropbox and the GitHub repository. It's probably mostly convenient to pull from the repository every so often. The key here is that the materials will be updated as we go through the week. People are introducing last-minute changes and things like that. But the reading materials should be there. We have a big table that I'm trying to keep up in sync with what's uploaded already. So you can see that for Bob's lectures, mostly all the materials are up there. And so you can see for the other lectures, you will see the changes here. Now, locations and venues are all here. And let me just, last thing to say is that we've posted the list of online participants with your universities on this internal page as well, so to facilitate networking. You're here to learn from us, we're here to learn from you, and you're here to talk to everybody you see around. Welcome again. And now I'm passing to Bob for the first lecture.
Great.
Ah, you have your own mic, that's right. I'll just...
Measure the slides.
Keyboard is on the other side. Here.
Can you guys hear me? Yeah, I think you can. That's good. So let's forget the slides now. Actually, you should turn to the slides.
There you go.
Great. You should use your own slides because that way you can annotate what's going on and correct all my mistakes on the way. Send me stuff at the end, right? So an introduction. Why are we doing structural econometrics? First of all, for internal consistency. In other words, taking a model and following it through logically so that the last step actually follows from the first step as opposed to something being made up. The rational individuals facing constraints, the rationality thing is more a statement about it's really hard to model how people are irrational. So in that sense, that's one justification. And another justification is if people are following patterns, well then with revealed preference theory, you can often construct a utility function. And so that's another kind of way of motivating it. Uncertainty being treated as part of a probability distribution, that's been going on for a while now, more than 100 years. And the equilibrium is a notion of coordination between individuals. So we somehow have to think about what happens when people do things that aren't completely in sync. They're not on the same team. The data generating process is going to come from, first of all, the model combined with the data, because the data is going to have some variables that are observed, and then there's going to be stuff that's not seen in the data. And the not seen stuff is going to be providing the reason why the observed stuff can't by itself rationalize what's going on. And hence, that's where the distribution is going to come from. And then the estimation, notice I've already said, law of large numbers, central limit theorem. We've backed off the idea, and I say backed off reluctantly, being able to get the finite distribution of what we would like to get the exact probability distribution, but we usually can't, and that's a pain. And so that's our retreat. So the next thing is the, I'm going to call it elegance and transparency. Well, elegance is, of course, is in the mind of the beholder. And when people talk about something that's transparent, I mean, what could be more transparent than least squares, right? You know, you just go plug in the x's, plug in the y's, get your answer. If that's not transparent, I don't know what is. Except that when people report least square stuff, they don't report one regression, do they? They do hundreds of them and then report the one that they like. Okay, and if you've ever done any consulting, you know exactly that's what people do. And yet you can see why there's an incentive to do that. And so to some extent, the structural part of being transparent is being able to see the steps that lead up to the data generating process. Another criticism that you'll get, and so to some extent, I'm not trying to be too defensive here, but to some extent you'll get people that say, doing structural econometrics, transparent, you're joking. Because basically they're thinking, you've got all these complicated formulas, and I don't want to learn them, and you've got a whole bunch of other numerical stuff going on there. How do I know? What's so transparent about that? And so that's an issue, because you want to be able to not just say this is an internally consistent structure, but you want to be able to demonstrate it. And that is a little bit of a challenge. Having said that, we have computer programs, they're potentially replicable. And so that kind of replication or possibility then makes the transparency sort of more possible. Okay? Causality is another reason why we think about what's going on in structural models. See, causal relationships for a structural guy like me only happen within the model. That's what causality means for me. I have a model that shows you start out with this stuff, and that's what you end up with. Now, there is another interpretation of causality, which I've sort of heard around. It goes along the lines of, I've got this great instrument. I run instrumental variables. Now, you tell me what's wrong with my instrument, because it's a great instrument. Notice how, with a causal relationship on my setup, I got to justify my assumptions. I've got to tell you why, even though this is not very real, it's worth taking seriously. Whereas if a causal guy gets up there and says, I've got this causal relationship and I've got this great instrument, it's up to the responder, it's up to the person who's listening to say, no, you haven't, I can think of correlation between here and here. A little bit of a difference that way. And it's something that we have to deal with, okay? You have to deal with. Don't worry, we've got our own set of armor. So in this setup, in a structural setup, the economic framework is based on explicit assumptions. You don't talk about, which I heard somebody talk about just in a seminar just a couple of weeks ago, high-level assumptions coming from different studies, different data sets, supposedly yielding the same conclusions. What do we mean by high-level assumptions and different data sets? What he really means is we've got a bunch of marginal distributions. Those marginal distributions are coming from these different kind of data sets. And the reason they're marginal is because he doesn't have the joint distribution. He's looking at this data set over here, that data set over there. Hey, what about the crosses, guys? What about the off-diagonal elements? Let alone the economic model. So that's the sense in which I want to talk about causality, not just me, everybody here that's lecturing will be talking about causality in that way. And that's the sense in which we can talk about counterfactual predictions. And ultimately, that's what economics is about. I mean, economics could be viewed as poetry, right? In which we sort of see this data and we put it together and we say, isn't that nice? Isn't that beautiful? But if we actually want to get paid, we have to do better than poets. And the way we do better than poets is to say, look, we haven't quite seen the world like this before. Can we take our model and ask ourselves, what would happen if we change some of those underlying parameters? How would the outcomes change? And that's where structural econometrics really comes into its own. Because as soon as the causality guys start talking about this causes that, this causes whatever, it's always within the one regime. Look, if they were dealing with different regimes, they'd have a problem, right? How do you make the comparison between two regimes if you're just doing causal stuff? It's not on. So that is the advantage that structural econometrics carries with it. And it's a kind of holy grail thing that we're still going for. And it's always going to be that way because causality is always, at least in this kind of interpretation, is always going to be couched in terms of the model that you're going with. One of the issues that we face, a big one, is the heterogeneity that I won't say infects, you could say enriches, inspires, complicates theory. I mean, economics is about specialization and trade, right? Different people having different objectives or different technologies that then lead to these interactions. That's what economists are supposed to be able to explain. And so it's even more complicated in dynamic environments. Notice how I'm automatically switching to a model-based sort of way of description because I start up the top bullet point in heterogeneity and then suddenly introduce this dynamics thing into it. Really moving it towards models, thinking about a model. How else? How else are we going to talk about patterns? Well, in that case, you've got all kinds of investment and all kinds of decay as well. Wait for it, guys, it'll hit you. And then in this process, there's this sequential revelation of information as people update and replan, if you like. So that makes it harder to do inference, of course, because not only do you have all these people coming from different backgrounds, but they're also learning different things because they come from different technologies, and you're trying to put it all together, okay? So how do we do this policy evaluation? First of all, I have no clue how to do policy evaluation unless you're don't have a model to begin with. I mean, you could just announce it, I guess. But then you'd be using polemics, rhetoric, and stuff like that to be able to say, this is what's going to happen, okay? And so maybe some of you want to be preachers or ministers or something like that, and that would be an alternative way of going about it. I've backed off that idea, for myself at least. Shouldn't the model's parameters be determined by the population under consideration? Of course. But that's the ideal, right? I mean, in medical experiments, they use lab rats and mice. Do lab rats and mice look like humans? Sort of. Now, they use it and they make decisions about stuff that might affect your life in terms of drugs and stuff that you might take, right? So when someone asks you next time, your model isn't very realistic, which is something you will get all the time, you just say, are humans like rats? Okay? Because they're already relying on rats. So why can't we rely on dealing with data that is less than a complete description of what's actually going on? There's a kind of sense about what is a realistic assumption. Now, let's be clear about what realism is. Realism is basically what people believe or have received. We've only got several senses to work with, eyes, nose, whatever. Okay? That's it. And then people write things down and maybe they're forgotten about. But think about how what we call knowledge evolves. Okay? It's really how we sort of talk about, communicate our senses or something. So if you're a researcher, your job is to come up with something stupid because you have to upset realism. You have to say, no, this is not the way we should be thinking about things. We reject the null hypothesis. Okay? That is the way you create value. If you're not going to do that, if you're simply going to reaffirm what everybody already knows, why should we pay you? Okay? And I don't just mean as a consultant. I even mean as a researcher or teacher. Now, I'm not the one that decides all that kind of stuff, but you've got to think about where is the social benefit or where is the benefit of what you're doing. So that's the sense in which research challenges orthodoxy. And we know that some of the strongest scientists, Copernicus, Galileo, whatever, have been punished for doing good research. Now, I'm not suggesting you go ahead and martyr yourself, okay? But you can see where I'm going on this. Where do we start on this? It's enough introduction. By the way, I'm going to be around at lunch. You should bug me if you want. And also, there's a 5:30 thing, right? Yes, the 5:30 event, which we're all going to, right? And yeah, we can continue to talk economics there. Questions, contradict me if you like. It's fine. So where do we start? With data. In our case, for almost all of this stuff that we do, we got data on individuals, background data, choices, and there's outcomes. See those three things? Got the input, background characteristics, and then model with background characteristics. They make choices, and then what are the outcomes? What happens? Why is this a hard thing to do? Why are you here? I mean, it's great weather outside. First of all, choices and outcomes of many of these economic models are often non-linear. And so that makes things a little bit difficult. Not only that, the data that we have is going to be an incomplete description of what we think's going on, let alone what our critics and referees are going to think. Okay. How do we go from there? Well, let's start with a prototype model. Okay. Discrete choice. This is where it's important for you guys. If you got the computers, you can always open them up and say, what does he mean here? Or this one's wrong. Feel free to do that. You've got some choices. You make one choice out of many. The fact that they're mutually exclusive is no big deal, at least at this point, because you can always put down all the possible permutations. And then after that, or at the time, there's a bunch of background characteristics. We'll call them Z in this country. Okay. And they're thinking about, person's thinking about, well, given my Z, let's see whether this works again. Given my Z and my choice, what is my next period Z going to look like? Transition matrix, dependent on both what I got, what I have, and then what I do. So it could be, maybe here are a number of births. This is not going to work very well for the 21st century, but think about it for a century ago. Number of births before now. I've got wages that depend on my participation, depend on maybe, I'll make it simple, the participation last year and the participation the year before. See, these are like 0 or 1, so this could be at least 2. And in fact, if you run a bunch of wage regressions, you typically find that wages depend on recent past work experience, plus education, a couple of other variables, okay? You do that, you get most of it. Or you can't get much more out of the observed stuff, let's put it that way. And you can imagine in the early 20th century, maybe up to 5, thinking about having up to 5, we'll call it live births, some levels of experience, no background, one participation, 2 participations, and maybe ages, because that might depend on things. You got 750 values, maybe some education, add in some education as well. Pretty soon you're driving it up to 9,000 variables of 9,000 values that those variables can take. So if we're talking about a transition matrix, well, you've got 81 million cells, okay? With a very, in other words, going from Z, taking a choice, what is Z going to look like next period? Matrix, right? So 9,000 by 9,000, there you go. Okay, first point is it's not quite that bad, because often we're going to put structure on what can happen. You can't have 5 kids at once. Well, very rarely. Sometimes it happens. And here we're starting to say, maybe we don't want to worry about those really unusual events too much. Why don't we want to worry about them? Because the people that are actually making the decisions probably don't think they're going to get 5 kids at once, putting a fairly low probability on that event. And so squishing the model down a bit and saying, well, let's only allow 1 kid at once. Let's not even allow twins. Well, that's really going to kill it down. That's really going to knock it down. And then there are other things. We already said that the capital that you have, which is the number of periods you've worked, can only be up to 2. So that's going to change things as well. And so if we did both of those 2 things, you'd actually have at most 54,000 elements. Look at that, 81 down to 54,000, 81 million down to 54,000. And not only that, basically they're sort of banded around the diagonal with the non-zero elements equal to 1. So thinking about the economics of the transition in a fairly simplistic way often helps you as you're sort of thinking about what can happen in the economic model, okay? Not everything. So that helps. So I do say at the bottom, then there's this italics thing. Modeling state space is an art or task for machine learning. Okay? That's a squishy statement, isn't it? But in fact, it is a statement about how you choose, how you as a researcher choose what you think is important as you move ahead. And the reason why it's important is when people evaluate your work, they're going to go for stuff like that and ask, were these reasonable assumptions that you could make at that point? And that's the kind of place you're in as you think about models. What's reasonable? What can we ignore? Where do we go from there? What do we impute? How do we use the machine? And if we're using AI or something like that, how trustworthy is it in the sense of how robust if we use different sorts of ways of going? And in fact, John was going to talk about that, and maybe someone will on Tuesday. All right, let's move on. We got an individual model here of dynamic choice. I talked about the choices itself, and now there's why does he or she make these choices? They're getting something called utility out of them. It's not really that we care about their utility, of course. We're trying to predict we're not social welfare workers. We're trying to predict what they would do in different situations. And so the utility stuff is almost a derivative or coming from a more primal, what do they do stuff that allows us to construct a utility function. In other words, this is how they behave. Revealed preference theory, utility function, that's sort of where that utility function is coming from. And so when we talk about utility, that's what we kind of have in our background. Notice there's a whole bunch of stuff that is sort of layered on in this particular formulation of it. See, this thing depends on your Zs. Well, what is that Z, okay, that it depends on? It's your background variable. Is it your whole history? I mean, in Slovenia, your medical records are just there like that, okay? And you can see it. And then you probably got the genetic stuff as well. And if we could understand the genes well enough, we'd be able to go back even further. See how many variables you're going to get. You start thinking about those genetic strands and see what kind of assumptions we're going to be making. Everyone else does, okay? Everyone else does. And in fact, sometimes we're told to ignore stuff like gender. Don't even think about it, guys. So there's a sense in which those choices about what we think are important are coming right through here. And the other thing to notice here is that once you start making choices like that in terms of restricting what you're going to take into account and what you're going to leave behind, you're putting a kind of additive structure in there. In other words, if you had that U depending on the whole history with everything in there, probably be fine, okay? Because providing people not making contradictory choices throughout their life, that'd help. This beta here is entirely redundant because we're already subscripting the utility by a time subscript. But the thing is, we want to be able to make sure that this adds up to something finite. We don't want to be adding infinity to minus infinity, okay? That's a really hard thing to do. And so that way, by sort of bounding things in that way or almost bounding them, we're able to get out of that problem. Throwing a geometric discount factor on there is a pretty useful thing. One of the things that is really questionable, though, is why we usually pick beta equal to 0.9 when we're talking about a yearly thing, 10% discount, subjective discount factor. Where is that coming from? After all, we already acknowledged that our model is very specific to the situation that we're looking at. It's not going to explain the whole world. So why that 10%? In different situations, maybe people are doing different things, even though that model is going to be contradict some other model. Remember, I was making fun of these people, this person who will remain unnamed, talking about high-level assumptions from different stuff and then using that to draw a conclusion. Okay, I can't see how you can do that. But equally, I then have to restrict myself to saying, no, I can't be that universal. This is as far as I can go with the model that I've got right now. That's why I'm going that way. And so in this setup, I'm trying to say, yeah, I'm going to put these assumptions on for this purposes of this application. I cannot fly to Jupiter yet. Can we just stick to Mars or maybe the moon? That's an important issue too. We'd all love to solve the whole world's problems, maybe, especially if we're a dictator. But given that no one in this room has that much chance of being one yet, least of all me, try if I will, you narrow it to something that you can do. And that's a sense in what research questions can your data really respond to? And how can you not be real? I've already debunked that notion. I said, how can you make money, right? That's what I said. And really, I was appealing to Adam Smith here. Because I was basically saying, look, if I can make money, that means it's good for the market and, you know, it also has social benefit. Well, I know that's a stretch because we can talk about public goods and externalities and all the rest of it. But you see where I'm going, I think. So this beta is in there as a help to keep that model mathematically under control. Person is maximizing this thing. Got till 10:30. Person is maximizing this thing, and the optimal behavior again is coming from the fact that they're making choices that we think are consistent in some sense, reflexive, transitive, at least. Okay, so obeying those axioms. Look, if they're not making choices that have those kinds of properties, first of all, we can make money off them, and that's really good, except that they will go broke pretty quickly, so we won't be able to make very much money off them, okay? So that's one thing. Second thing is, how would you be able to think about modeling somebody who doesn't have preferences that more or less obey those kinds of rules? Because they're doing inconsistent things all the time. Where is the replication that we're going to be able to use to be able to make any inference? Okay? That's the kind of stuff we have to worry about. So this guy's optimal, okay? He's making decisions that follow a consistent set of preferences. Notice this D little o, meaning optimal decision making, is just going to take on a 1 or a 0 for everything, but just one of the actions, which will be the optimal one. So really, we're just summing over the path of utility that he gets when he takes, the optimal action. All follow? And so that's what we call the ex ante value function, or sometimes social surplus. At this point, I've just talked about Z's. I haven't introduced unobservables or observables yet, right? These are just background variables. So yeah, social surplus is a little bit of a stretch, but we'll come to that in a minute. A social surplus probably applies to something that is a little bit more narrowly defined than this one is. So in terms of the next period, just to remind ourselves, we just put a beta out the front, we put the expectation there, and the reason I'm putting out that next period's value function, of course, is so that I can appeal to Bellman, and my suspicion is that many of you have already seen this, in which we've got the value of lifetime utility from, say, here on out. This is time period T with backbound variables Z, all the way out. And so you get utility to this period, and then you get utilities from all the next periods. Depending on the choice you make, that's going to affect the Zs that you got to get next period, et cetera, et cetera, et cetera. Okay. And then, of course, we just plug in, for this part, from the previous slide, discounted value of next period's lifetime utility now expected over what your background variables will be at that time, given that you took the optimal action to date. So that's what we often use when we're moving down this kind of route towards inference. You know, you could solve this model in principle. And here I want to point out something else. It's like, why not? Why not solve the model in principle for every possible Z? Why not do that? Okay, we've got computers. And my answer, of course, is going to be that computers are pretty good. They're faster than us in lots of things, but they still don't do everything. Okay. So in principle, we'd start out at the bottom, the very last period of the person's life. Maybe that is actually stochastic. We don't know when it's going to end. Maybe there's a bequeathing utility as well, perhaps, that we tack on at the end. But basically, we go from there, solve out for the last periods, get the optimal action in the last period, plug that in, keep working backwards, we're done, okay? And even if we were doing something that lasted out to infinity, because these betas are dying off at a geometric rate, we could solve out for a finite problem, and we'd be pretty close to the optimal one. This is the solution for the infinite horizon problem. Notice I haven't really appealed to stationarity here, but we could potentially do that, okay? Providing the U's were bounded. So how would we go about estimating this model? We got some background variables. We've got a way this person is going to behave with those background variables. We've banged on optimality. So we've got consistent pattern here. We've got the beginnings of a way of thinking about what does his or her preferences look like, okay? So let's imagine that, or not imagine, let's define this VJT, and I'm not going to call this a conditional value function, not yet, okay? Because I just got Z's in here now, Z's. I don't have any unobserved stuff, they're just Z's, okay? So I got this current utility and the future lifetime utility. And because they're behaving optimally, they're going to choose the J that gives a bigger bang for buck than all the K's. All right? That's how this choice is going to be made. Choose the biggest one of these. And suppose we've got a bunch of people now. We know all the characteristics, maybe all the histories. And we see them, maybe from when they start to when they end, all right? A lot. So what can we do? First of all, we see what happens to them when they make choice J, for whatever reason, given they have background variables ZT, ZT, okay? And we see what happens to them in terms of, well, let's keep Z finite, can we at least? Make it a little easier for us. Almost all the stuff that I'm going to be talking about today is in a finite space, in other words, finite number of values. It's not that moving to a countable space or even a bigger space than that causes that many problems in principle, because you can always smooth. And so providing things are in some sense comparable so that you can talk about what we mean to smooth, right? You can't compare black with white unless there's a way of sort of mixing those colors together. Gray, maybe? That's a sense in which we could move to a bigger space. But I don't want to deal with the math here. And in fact, so much of a computation is finite anyway. There's not that much point, but at least for now, principles carry through. So we've got these lots of background variables, produce a second set of background variables depending on the time period and the J, the choice you make. And then there are all these people that are making these different choices, okay? It's wonderful. Cornucopia, the world, all right? Making different choices with their background variables, their choices, and all the rest of it. Why don't we just put it together? Because after all, we've got all these indicator functions, right? A whole bunch of inequalities. Put them together and go from there, because then we'll be able to infer what people's preferences are like. And some people still do that in econometrics. Some people, well, they call it econometrics. It's more like mathematical programming. But putting together all these inequalities and saying, okay, what does it tell us about? What does it tell us about those preferences? Maybe we could do that. Well, 1 or 2 people in the data set have the same age, say, and the same set of background variables, but they make different decisions. One makes a decision J, the other one makes a decision K. Well, what can we conclude? Must have had the same utility, right? Some of them went one way, some of them went the other way. Why would they do that? Because it has to be true that they're indifferent between going one way or the other, okay? Now let's imagine our world is pretty big, okay? You've got a finite number of choices here, lots of people with the same background. How many choices are we going to see that are the same? It would not surprise me that in most data sets, for most of the models that we look at, probably all of them, we would see every choice being made given the same time period and the same set of Zs. You all follow? Because we will see that some people do this, some people do that, some people do the other thing. They all have the same T, they all have the same ZT. Why, what's going on here? Okay, we have to conclude from the model that they're equally well off doing that. Well, what are we going to be able to predict from this model? Nothing. Okay? It has no empirical content. Okay? How valuable are economists that can say anything can happen? 0. Okay? People are not interested in hearing that kind of stuff. They want to know how to make profits. They want to know how to make their life better. They want help. This is not going to help them. Okay? Now, this is a good time to talk about the British Museum. It's not very far away. And if we're thinking about data, people digging up archaeological data, how did man evolve? Not very many observations. Get out there like Indiana Jones, discover a whole bunch of stuff. I mix up my fakies and my reals. And then you put it together, jigsaw puzzle, put the pieces together, and you've got a history of the world. That sort of works. And that's what people were doing for a long time in terms of thinking about how do we understand ourselves? How do we make predictions? Get different pieces, put them together, and then come up with a story. I mean, it's not like my stories or anybody, I won't talk about the other people, but at least the models that I estimate are any more than stories that somehow fit the data. Okay, I already said, forget this reality stuff. I already said, let's just try and get something consistent so that we can help a little bit. So if you don't have very many points, data points, that would be a natural way to go. Okay? And I would say it was for quite a while. But then people started to record history a little bit better, or well, a little bit more systematically with variables and numbers. And pretty soon, in the middle of last century, and a lot of people give credit to Habermas for this one, said, nah, this is not going to work. We're going to have to introduce unobserved variables as well as variables. as well as observed variables, because if we stick with observed variables and go through with this exercise, we end up with, they would put it contradictions. I would put it no empirical content. Either way, you're not going to get very far. And so that's the sense in which we think about why unobserved variables have to be introduced. They are not making things any more complete. We do it because we have to. Otherwise, we're stuck with saying anything can happen. People usually introduce things like unobserved heterogeneity as some kind of extra thing they can just gratuitously add. Bullshit. They need that unobserved heterogeneity in there in order to be able to get somewhere. And of course, as soon as you introduce unobserved heterogeneity, you have to think about, well, what are those variables that we don't observe but that we think are important? How do we deal with that? So that's the problem that people face. There is another reason why they do it, though, and it's the last bullet point on that slide. See, if you say that we're going to look at people who just exactly do one thing or don't, and then you have a whole bunch of contradictions, so you get frequencies of people doing one thing or another. Notice I haven't introduced statistics yet. Frequencies, histograms, that's what I'm talking about here. Well, don't you want those histograms to reflect that 99.9% of people do one thing and only the, 0.01% do the other thing? Don't you want to be able to handle that? You want to be able to give sort of more weight to things that happen more often. Okay? You go back to your measure theory and you think, what's going on? Weight, right? It's all about weight, probability, okay? Same thing. So that's the sense in which just looking at the decisions of the individuals as opposed to groups, fractions, is not going to be very profitable. So let's back off again. We're just going to look at the probability distribution of choices, margined out, that is, integrated over the factors that individuals observe and take into account, but we don't. Now, this is the sense in which, by looking at the behavior of a population, we are obliterating the difference between macro and micro. There really isn't any difference between the two so-called disciplines, except we do it right. Okay? So that is where we're going here. Okay? Because we're acknowledging that there's a stochastic process. We're acknowledging there are variables that we don't observe. We're going through thinking about the distribution function after we plug it in and go from there. Richard Blundell. Some of you guys would surely know him. Talking about students here, we all know him. Once related an anecdote to me quite recently. He said my macro teacher, Robert Lucas, you've probably heard of him too, said to Richard, I don't need a magnifying glass to know what's going on. And of course, what he was referring to is how much heterogeneity do we really have to understand and see before we can make predictions about what's going to happen in the aggregate. That was his comment. But the comment was made many years ago as a way of dismissing structural applied micro. So much more recently, he was kind of more friendly, kind of more accepting. Macroeconomists are learning slowly. Okay? How would we go about this? But we're all brothers and sisters of each other, right? All in a happy family squabbling together. Right. So I want to distinguish between observed variables and unobserved variables now. Okay? Those are the epsilons. I'm not putting any structure on those epsilons yet, all right? Don't think logit type 1 extreme value yet, please. Okay? It's just something that we don't observe, that individuals take into account when they make decisions, but we don't. Okay? How would you go from there? Well, basically, you ask, what is next period's set of background variables going to be? Background variables consisting of the stuff that we observe and the stuff that individuals themselves observe, but we don't observe. And it clearly depends on what the background variables are today and also what action that we take today, which is going to be optimal. So here's our optimal action, okay? And here's our transition that's going to drive that. And so now we could put all this together. Some of this stuff you're going to have to take on faith from me because I'm not going to go through it in detail. We're going to integrate over all those epsilons starting from now, first period of life, ending later. And we're asking, given my set of background variables that I observe as an econometrician, what is the path of all the choices that are going to be made throughout the life of the individual, along with the background variables that they will get through that time? Joint distribution. Forget about these high-level assumptions and marginals. Joint distribution, please. Okay? I seem to have that guy on my mind. So we're integrating over all those epsilons. Okay. And then we're asking, how does that transition from one to the next? Well, the first one is basically, well, I see my x's, what am I going to do? And then I'm producting everything else and asking, well, this is the joint distribution of whatever I got conditional on, this is the joint distribution of what's going to happen to me tomorrow given whatever I got today. Product, product, product. Okay, that's where that product thing is coming from. Put it all together. That then becomes the joint distribution of seeing the lot. So how do we go about this? Well, let's suppose we can index the utility by a theta. And when I say index, what I really mean is exponential utility, relative risk aversion utility, blah, blah, blah. Okay? With a few parameters and a bunch of x betas up the top or around there to control what's going on. In other words, I'm thinking of a theta that sits in a Euclidean space. Okay? Vector. And that way I'm making it easy for myself. See, why would people make things easy for themselves? Maybe when we go to someone like Mr. Trump, I shouldn't introduce political stuff in here. We should just say, here's the data, sir. And he will say, I'm very smart. I'm a genius. I can analyze the data for myself. Okay? And go from there. That's the complete set. So whenever we do anything that involves some kind of parameterization or taking things down, data reduction is really what we're doing, okay? We're taking the data and putting it in a form that it can be interpreted within the model and the assumptions that we've made, okay? We're actually saying, look, we're going to make these set of assumptions. If you think about these set of assumptions, well, then this is how we interpret the data. And in those kinds of situations, we might even be able to talk about sufficient statistics and stuff like that. Okay? So that's really what that theta is doing. It is layering one more set of assumptions on the additive part of the utilities that we've already looked at and we've already put in, okay? I said, remember we had the u plus the beta u plus the beta squared u. That's one set of assumptions that we're making, sort of a kind of additivity, especially if when we pull down the z a little bit from the complete history to some chunks that we're going to think are important. You know, think about that life cycle example with just the way the wages turn and the births and all that. So we imagine, because we're structural guys, we imagine, and it's not that we believe it. You don't have to believe anything in the world that I live in. It's just a matter of going with something to see the next day, bread on your table, money in your pocket, whatever, okay? We imagine that this data was actually generated by the specification that we're laying out. We say, put aside all your doubts for a minute and pretend that this data was generated by people that live in the world that I am specifying. I think it's really hard to do anything else with data, by the way. Obviously, otherwise I wouldn't have been doing it for the last 45 years. But, so we go ahead and do that. And then we ask, here are all the things that happened. How do we maximize the probability of, by choosing our theta to make that the most likely thing? That is no different from the way judges go around convicting criminals. They look at all the evidence, apparently. Questions about the Supreme Court today. They look at all the evidence, okay? And then they say, sort of beyond reasonable doubt. In other words, innocent until proven guilty. H0 innocent, but HA is that innocent hypothesis doesn't hold up because there's too much evidence against it. That's how they're actually doing things. And in a sense, classical statistics is not very different from that. Now, if we were Bayesians, we could say, we've got this huge view of the world, and we're just going to use data to narrow it up, okay? But as classical people, we don't usually do that. And whether we're Bayesian or classical, in the end of the day, doesn't make that much difference. Okay, so people have done this, Ken Walpin and I, on different things, job turnover and fertility. And of course, it's an incredibly complicated process because you can imagine solving this stuff out with all this unobserved heterogeneity in there, integrating everything out. See what you've got to do? Here are these integrals. That's a lot of work for the computer, okay? And so what you do to pull that off is make a whole lot of extra assumptions in order to make the model sufficiently simple so that it's computationally possible. You're always going to have that trade-off. Always going to be that. And go ahead, get the maximum likelihood estimators out. Ariel, who's going to be talking later on, said, we don't have to really integrate everything out. Why don't we just simulate out paths? Because after all, when we do estimation, we're already averaging over outcomes. So why don't we just push out the paths and average over those whole paths? So that seems like a promising way of pushing forward. And then Victor has further worked on this, and he's going to be talking about fixed effects tomorrow. I'm going to be talking about thinking about multiple integration, cheaper ways of doing that tomorrow as well. But John said, hey, wait a minute. Do we really have to have that much unobserved heterogeneity in the model? Can't we do something a little bit more straightforward, guys? Instead of integrating over this unobserved heterogeneity that feeds in period after period, so that you have to do all this integration, why don't we just bam it down so that it's only hitting current stuff and not having too much effect on the future? Okay, so what does he do? He says, all right, here's our joint distribution, okay? Depends on J, action you take, depends on the unobservables, and here's what's going to happen. Why don't we assume, first of all, the observables themselves just depend on the action you take and also the state of the world that you're in when you take it. The state of the world that the econometrician observes when you take it. All right? So it's the x's. Notice there are no epsilons in there. And in addition, let's suppose that conditional on knowing the state of the world next period, well, then we can talk about the distribution of the unobservable. This one is not such, yeah, well, no, it counts. But we'll assume that as well. Okay, in that way, the unobserved variable, conditional on the observed parts, is independent. All right? So this assumption, widely used, almost not universal, but very widely used in the estimation of dynamic discrete choice models. Okay. And I would say that with bigger and bigger data sets, that conditional independent assumption is going to be around for a while because we got more and more variables that we can condition on. And so if we're going to make our models more complicated in order to deal with increasing distances, you know, I said I can't fly to Jupiter yet, maybe Mars. Good luck. But we can definitely get to the moon. So as we push our horizons out in terms of what we think we can deal with, you can easily imagine a situation in which we'll be wanting to include extra variables, extra components in that vector that we actually can deal with, as opposed to pushing for too much on the unobservable stuff, which is not to say it should be ignored. I really don't think so. But that's me speculating. Let's move on because you don't want to hear that too much about speculation. So let's imagine we got conditional independence, okay? We've got this discount factor. And we've got the utility being the sum of observed stuff. Here's the observed stuff, plus this epsilon. That breaking up into an additive part is not really a big assumption because we're really just taking a conditional expectation of the utility, conditional expectation of u x comma epsilon, right? Conditional on x plus what's left over gives you this additive decomposition. So that's not a big deal. And of course, we want to put some bounds on the epsilons too, so that they don't lead us into the plus minus infinity problem. So let's do that by just taking absolute values and stuff and integrating over that possibility. And so now what we've got is almost the same problem as before. It is the same problem as before, but now it's a little bit specialized. That's what's going on here. We've got the utility of the person depending on what everybody observes, including us, plus what they observe, but we don't observe. And we also have the fact that what they observe, but we don't observe, follows, oops, this this assumption, okay? The epsilon really doesn't depend on too much. We need that unobserved heterogeneity in there for the reason that I talked about at the very beginning. We gave up on the British Museum, okay? So that's why that's in there. And now we can talk about the optimal, about the social surplus problem. It's easier to define the social surplus problem when this assumption is satisfied. I'm not saying you can't do it, but normally the social surplus function is defined for these kinds of problems, because actually it comes back to discrete models from McFadden when he was talking about social surplus. Again, he was talking about what's observed, what's unobserved, and of course it was a static model, so one period, so there was nothing to go on, so you didn't have to worry about that. So this is a natural kind of lead out here. The ex ante value function with the utilities in here, you see the x's, you're integrating over everything else, and you're asking, well, okay, what's the expected lifetime utility? Now I want to define what we'll call the conditional value function. Some people call it, I think, the choice-specific, choice-based value function. So it goes by a couple of names now. And it's the utility that you get from taking a given choice without the epsilon attached to it. See that? Epsilon is not being attached to it, so it doesn't give you the whole utility, lifetime utility, but only this part of the utility, as well as next period's expected utility. And for that reason, then, this thing does not depend on x and epsilon, it only depends on x, okay? And that's going to be key later on. And so now we can talk about, in this context, conditional choice probabilities. Again, we could extend that definition, but let's leave it this way for now. The expected value of the choice, or the probability that a choice gets made, same thing with this binary variable, okay? Then it'll be choice J, given that the x's you face, and here we're just integrating over the epsilons. Actually, you can push this out to a dynamic game. And this is part of what Victor will be talking about, I think, on Wednesday. Suppose now you've got a bunch of players, okay? And here are all the choices that people make. Here are all the choices that's the individual, all the choices that I makes, all the choices that everybody makes, all the choices that everybody but I makes, okay? Because you're always best responding to what everybody else is doing, right? In these kinds of, I'm going to call it Nash equilibrium, Markov perfect. Set of state variables, a transition matrix telling you this is what happens to the state variables, given the state variables are xt today, and people make these kinds of choices. We're already assuming the conditional independence assumption at this point. And so this is just the probability distribution for xt plus 1 given xt, and the choices that everybody apart from you, here's the choice that everybody makes. Here's the choice if they make a set of choices and you make a J choice. Then we're talking about the transition of you making your own choice, everybody else making their equilibrium choices, okay? So now you can go ahead and sum up. You've got utilities that you're getting not only on what you do, but also on what everybody else does. And if we go from here, we've got the conditional choice probability for Mr. I choosing choice J with his state variables, just integrating over the choices that I make, or Mr. I makes, over my epsilons. Okay, so it is really the same thing. And we can then talk about, well, what about everybody else? Well, they're part of the transition function. We were talking about it a minute ago in the single agent problem as nature. You know, I make a choice, it's xt and then xt plus 1. That's just nature, right? Doing its stuff, and that's why things are not perfectly anticipated. Now nature includes the other players as well, okay? And so that's why they get in here. This is the probability that everybody else makes different choices. Go from there. That means that the expected utility that I will get at the end of today will depend on the utility that I would make if everybody else did this. But I don't know what everybody else is going to do. But in the data, I'm actually going to be able to see what they did do with the different probabilities. So I put that together and I get my expected utility from making a choice J when the variables are xt. And likewise, the transition can be put together by thinking about, here's Mr. I, what's going to happen to him? Well, he makes choices. Actually, this shouldn't be an I, this should be the whole thing of xt there, so scrub that I out. And so this is going to then determine what the state variables are going to look like with the different types of probabilities, given the choices that I make. So how would we do this? And then what we would get is, well, this utility is exactly what we had before, almost, okay? A little u. This is the little f that we had before. And so in this setup, this best reply function is just the optimizing behavior for the individual. And you go from there, okay? And so that's the sense in which these Markov games fit right in that context for the individual problem. And so learning about the individual problem is a pretty good introduction to thinking about what would happen in a Markov perfect equilibrium and when you're trying to do inference from there. All right. How do we go ahead and do this? You know, seems appropriate to take a quote from our great leader. How should we solve this? Well, there are a bunch of ways. Do we integrate the model solution into estimation routine? And Bertel and Fyodor are going to be talking about pretty moving ahead on that front after lunch. Get a maximum likelihood estimator out. Okay. That way you get asymptotic efficiency. And the fixed point algorithm that they're going to do is double as a solution to counterfactuals. Okay. In other words, once you solved it for the estimation, you can, of course, solve it for doing the counterfactuals. So that is definitely one way of going about it. Or you could actually separate the inferential problem from the model solution. Look at the data generating process, determine whether the thing's identified or not, then get the estimators. You're going to get some identification conditions. You can use those identification conditions, perhaps by themselves, not have to solve the model, go from there. You won't have to actually solve the model in when you're doing the estimation. To do the counterfactuals, typically, yes. I'm going to say typically, yes, because in the conference, and I'm hoping you guys all show up at the conference because you will get more out of it than the faculty. I shouldn't be on mic, but it's true. I want to talk about situations in which you can actually do some counterfactuals that are worthwhile, even though you're not resolving. But even if you did have to resolve, you'd only be resolving once or twice. And you'd be in the sense of just solving for the counterfactuals. And that way you can afford to let the computer run on for a longer time to get the counterfactuals out, as opposed to have the computer run lots and lots of times when you're doing the estimation. Okay, so even though the programming is going to be similar, obviously won't have to be as efficient if you're only doing it a few times, there are still some edges of which way one goes. And it's going to depend on the problem. Well, we can abandon statistics altogether if you want and just disconnect the sample variation from the probability, population probabilities. Just dispense with that. take some published work, go from there. Enough said. People are going to squabble about which method's best. There's no reason why they shouldn't. After all, we're trying to move forward here. You would think that there will be disagreements, and you would think that that's the way that academic discussion should go. And, you know, the only thing that I'm going to say is, what kind of data have you got? How complex is your model? How sensitive are your estimates to underlying assumptions? Is a sample of variation an important factor in assessing precision? And what is your specific policy question? Those are the kinds of issues that I think should be raised in the context of this discussion of which method should you choose, okay? Since John's not here. I was going to do it anyway. He doesn't like presenting Harold Zerker, but it's a good model. Here's Harold Zerker. He's thinking about either replacing the engine or maybe bus mileage you'll move just on, it'll just move one period ahead, okay? In the sense that put on 100,000 miles or 1,000,000 miles or whatever buses do in Madison each period, okay? In this case, I'm going to vary it a little bit. They're going to be not just GM buses, they're going to be GM and Ford buses, because this is going to be a Monte Carlo experiment, okay? And there are these choice-specific shocks that are going to be logit type 1 extreme value, gumball, you know, various names. And the conditional valuation function for each choice is going to be, well, either you replace the engine, J equals 1, in which case when you replace the engine, next period you're going to have 1,000,000, whatever, on it, okay? Or you don't, in which case you've got X going up by 1. And in that case, you've got to do some maintenance. And that's what it's going to cost you. It's going to depend on the number of miles you got and also kilometres, excuse me. No, miles for here. I don't know. And then Ford or GM, okay? That's the S part. We all come from different parts of the world anyway. So you should get to know each other, because a lot of you will continue to have interactions with each other as colleagues. Many of my colleagues I've known for decades, but I also get to know people as they come through. So you sort of accumulate this. The fact that you're all here, though, means that you're sort of motivated. I mean, very well motivated. Suppose you've got a cross-sectional thing, okay? Fixed engines, actually not just N observations, and you got the engine miles on it and the maintenance decision. We're going to assume that this is all stationary, not going to put too much time into it. No calendar years in this yet. I'll talk about that in a minute. If it was stationary, you would just have, well, what's the probability of making choice 1? Remember, choice 1 is replace engine. Choice 2 is keep the other. Keep it. This is just probability of replacing the engine, integrating out over these idiosyncratic factors. In other words, everything that we don't observe, that's the unobservable. Given it's a Ford or a GM, given the number of miles we're on it. Well, look at this. This is V2 plus epsilon 2. This is V1 plus epsilon 1. Okay, so you're just comparing the conditional value function plus the epsilon for each of the choices and taking the biggest. All right? And all I've done is put the epsilons over on the left-hand side there. So that's the inequality that has to be satisfied in this case. And in this case, this has the logit formula because we've got type 1 extreme value. We know that one for a long time ago, Big pattern, or earlier. And so you could form a maximum likelihood estimator, providing you knew these V's, okay? So the only difference between the McFadden, John's supervisor, and John is John says, hey, wait a minute, we can go dynamic, and here's how. All right? And that's a pretty big jump. So you've got these conditional value functions in there, but you've got to solve them or do something about them. Previous lecture, excuse me, guys. Some of this is taken from my Carnegie Mellon graduate lectures. Oh, sorry. I'll just say it is true that with a type 1 extreme value, and John proves this in his article, by the way, but you can go more general than that. I'll give you a couple examples later on. The social surplus function is just the conditional value minus the log of the probability. This is worth thinking about. I've only got 10 minutes, so I can't really talk about it now. But ask, why would the probability go up or down? And then we're getting the difference between the ex ante value function and the conditional value function. Just think about that one. The probability is high. Well, what does that do to this and this? You know, how does that change? All right. But just going back to the math for a minute. Conditional value function of not replacing. Well, this is just the V2. Well, there you get paying your maintenance cost plus your discounted value stuff. And so you're plugging in for V, this one for next period. See what I've done? I've said V is equal to this. And so plug it in here, but moving miles on by 1. And similarly, if we looked at V1, well, that's just from the previous slide, I think. Well, yeah. That is just equal to, that's coming back from here somewhere. If I can't find it, don't worry about it. Yeah, here it is, V1. This thing is equal to that. Well, what is this thing? Again, use this formula, put it in there. But bus engine miles is the only factor affecting bus value given S. It's the only thing that affects value from that. So if you replace it with whether it's got 1 mile on it or X plus 1 miles on it, doesn't matter. You're starting with a sort of reconditioned bus. And so the reconditioned bus is going to be the same. And you know, you pay a different cost, but you end up with the same set of state variables. You know, you replace a bus after 5 years, you replace a bus after 6 years. What does the new bus look like? It'll look the same. All right? So that's useful to know because we can now do some cancelling here. All right? So we can get rid of this guy, get rid of this guy. Look at the difference between V2 and V1. Okay? Remember I said what we need to do our maximum likelihood estimator somewhere or other, I'm trying to find it, is where did I want to do that logic? Right here, okay? V2 minus V1. I need the difference between those conditional value functions. That's what I want to get at, all right? And now I'm saying, yeah, maybe it's not that hard because you got V2 minus V1 here. You get rid of this guy and this guy. Well, what do you got left? You got this stuff here. You've got these two things cancelled. Don't have to worry about that. Pretty much done. So V2 minus V1, as I've just explained, put in the conditional choice probabilities. Okay, here's your P1 thing. This, if you solve those functions, would give you the maximum likelihood estimator. Let's not. Let's just put in this in terms of the probabilities and still do our logic. Okay? So instead, what we're doing intuitively is replacing the CCP for current replacement is the same as a static model. would be the static model if it didn't have this stuff in there. So that extra choices, those probabilities, are reflecting the difference in continuation values depending on where you go from. You know, you're saying, all right, this is not a static model. People take into account the future. How do they take it into account? Well, they solve their optimization problems. We get the conditional choice probabilities out, say, and then that will tell us a lot about the conditional value functions. And so instead of putting the conditional value functions in there, we put the conditional choice probabilities in there. Now, I just described it in a very intuitive fashion, which had absolutely no math, but I've already showed you what the math does. It is what I said, okay? So that's how we could go about it if we wanted to. So consider the following. This is what I'm going to talk about later, as in after break. Put together a sample, the cell estimator for the probabilities, okay, for replacing the bus engine. Plug them in here. Go ahead and estimate this thing. I'm going to say quasi-maximum likelihood, pseudo-maximum likelihood, fake maximum likelihood. I don't really care, all right? Going to put them in and then correct the standard errors. I'm going to estimate not just the theta 1 and theta 2, but also the beta, okay? If we do the theta 1, theta 2 without the beta, it's a little bit too easy. And then go from there and do the logic, all right? Well, I've done a Monte Carlo on this, so in the last 5 minutes, I'll give myself 5. You guys took a little bit after 9:30. No. You got these two, say you got half Ford, half GM, say, make it simple. Total accumulation is not just going to be 1 each period, but a random number where it's going to be drawn from this. I take the exponential distribution and then just break it up into pieces, okay? This many of them, okay, where you're just taking the sort of the difference in the cumulants in order to do that. And you've also got a root distribution. It's going to, the x2 being drawn from, you know, some buses do long routes, some do short routes, stuff like that. You've got some other maintenance costs maybe, and we'll let this depend on T now. It's kind of worthwhile spending a minute on because now we've introduced a non-stationarity in the model in a pretty big way. We've said costs vary by time period. And the agent, Mr. Zerker, knows that, and he's dealing with it, okay? Now, admittedly, in this framework, he not only knows what theta t is, he knows what theta 1, he knows what theta t plus 1 is, theta 2, etc. Okay. So there's an issue there as to how we think about that. The t has to be a sufficient statistic for what's moving forward. But given that, we could go ahead and say, well, we can allow for these differences over time to occur if we wanted to. Whereas if you were going to think about modeling the whole distribution likelihood, you would have to put a distribution on that one too and think about how you were dealing with these, in this case, aggregate shocks. So go ahead, you'd look at the difference between the conditional value functions. Suppose after 25,000 million miles or whatever, they're the same. Estimate the thing. So this is what we did. This is Peter Astiakono and me. And this is like 2005 or so. But I do get my graduate students to run these kinds of exercises with things that are about as complicated. And the difference is much, both estimate much more quickly now, but there is still a big difference between the maximum likelihood and Manuka's right here. he will confirm it, partly because he's my PhD student, but partly because he will speak his mind anyway, I hope. So there is a difference. There's not much difference in terms of the estimates, okay? Standard errors may be a little bit higher on this, as they should be, because after all, this one is maximum likelihood, and this is only a CCP, all right? But the main difference is between the amount of time it takes. And it's no surprise that if you're solving the model, it's going to take a lot longer than if you just are doing those plugins. Now, obviously, this is a pretty simple example. John did it almost 40 years ago. Actually, he would have done it 40 years ago, published, later. So there's still a question of, once you get into more serious Monte Carlos with more detail, how do these different estimators perform under those circumstances? What's reasonable, what's not? But I would be arguing that even if you're doing maximum likelihood, starting out with a consistent estimator, albeit with weak data, is better than searching all over the grid, because that's what you have to do, because there are very few nonlinear criterion functions that you're going to be able to prove a concave. You won't. And so then the question is, which space you're looking at, really? And so starting out with something that is sort of puts you in the ballpark is a reasonable way of proceeding. But for now, 10:30, lots of arguments and discussion to follow. Let's stop. For when do we start again? In 15 minutes, we'll start again. 10:45. 10:45.